Welcome back to the next video, everybody. Today we're going to be filling in a gap from the proof from the last video by looking at the torsion of elliptic curves with good reduction. So let's get into it. Last video we motivated the flat deformation functor by appealing to the p-adic Galois representations attached to elliptic curves over Q. However, there was a gap in our proof. We implicitly invoked the following non-trivial theorem when attempting to prove the ordinary reduction case last video when we appealed to the theory of p-divisible groups. So here's the theorem we actually have to prove. Theorem 14.3.2, let E over QP be an elliptic curve of good reduction. Then for all m not equal to 0, the QP group scheme E bracket m is the generic fiber of a finite flat group scheme over ZP. In fact, I can tell you what that scheme is. It's the M torsion of the Neuron model of E over ZP. Okay, so let's get into this proof. Let E sub Z sub P denote the Neuron model of E over Q sub P. Oh, by the way, we also used this theorem in chapter 1 at some point. I don't really remember when exactly, but I have a vivid memory of it. We know from the Bosch Neuron model book that E sub Z sub P is an abelian scheme of relative dimension 1 over ZP. To conclude, it turns out that it suffices to prove that, given an abelian scheme A to spec R of relative dimension D over an affine Noetherian base, the multiplication by M map, M sub A from A to A is finite and flat. Why is it enough to show that? Well, if we can show that, then the base extension by the identity section of A base changed to R shows us that A bracket M to spec R is finite and flat, which is what we're trying to show. Okay, so first, we'll note that M sub A is certainly proper. I'll let you check that. It's also quasi-finite. That can be checked on geometric fibers over algebraically closed fields by Mumford's abelian varieties, for example, page 62, for general abelian varieties, or if you want an argument for just elliptic curves, you can consult Silverman 1, chapter 3, proposition 4.2a. Okay, so anyway, so M sub A is a quasi-finite proper map between Noetherian schemes. So by e.g. for 8.11.1, M sub A must be finite, which is what we're after. In particular, M sub A is also affine. Okay, so we got the finite part, now we need the flatness. To prove flatness, note that since A to spec R is flat in a finite presentation, by the fiber-wise criterion for flatness, you can see EGA for 11.3.102, for example, for this. It suffices to check the flatness of M sub A along fibers over spec R. This means we can assume that R is a field, and in fact even algebraically closed, and the reason for that is that field extensions are faithfully flat. Okay, so it's not like we're losing anything by specifying. By Mumford abelian varieties, page 62, MA is a map between two smooth irreducible varieties of the same dimension D over an algebraically closed field, with fibers over all closed points of dimension D minus D equals 0. So by the local criterion for flatness, such a map must be flat. You can see Matsumura, commutative ring theory, theorem 23.1 for that. Okay, so we proved the theorem. The converse to the theorem also holds, although we won't need it. Let's talk about that for a second, though. If E bracket P to the R is the generic fiber of a finite flat group scheme over ZP for all R bigger than or equal to 1, then it turns out E over QP has good reduction. This is a special case of Grothendieck's theorem on p-divisible groups, which says the following. An abelian variety A over QP has good reduction if and only if its p-divisible group gamma has good reduction in the sense that it is the generic fiber of a p-divisible group over ZP. This is essentially the analog of the Neuron-Ogg-Shafarevich theorem at P. So I've been emphasizing this as far back as chapter 1. Neuron-Ogg-Shafarevich only works at primes away from the prime P in consideration. Okay, we have an analog at P given by Grothendieck's theorem here. All right. Okay, so you can see SGA 7.9 corollary 5.10, for example. Now, to apply this theorem, we need to invoke RSG. This is a theorem of Raynaud. Theorem 22.3.1, which says that Grothendieck's criteria is equivalent to the seemingly weaker condition that each torsion level of gamma is the generic fiber of a finite flat group scheme over ZP. Why is that a priori weaker, seemingly anyway? Well, we don't need to assume there's any compatibility between the ZP group schemes for each p-power torsion level. That's like there's no compatibility assumption. Okay. To use this converse, there must be a condition on the large torsion levels, as the first part of the following example shows, so this is kind of an important thing. Well, not really for us, but it's important conceptually. E over QP can have bad reduction, so that E bracket P to the N is not the generic fiber of a finite flat ZP group scheme for some large n, even while E bracket P does have good reduction. Okay? You can't just be like, oh, at the base level, I have good reduction, so all the way up the chain. Nope, that's not how it works. For example, let E over QP have bad split multiplicative reduction with non-integral J invariant of pth power and QP bar cross. The theory of the Tate curve then shows that rho bar EP is isomorphic to omega plus 1, where omega is the cyclotomic character, which is the GP representation attached to the generic fiber of a finite flat group scheme over ZP, namely mu P cross mu P times Z, the constant group scheme Z mod PZ. Okay? So there you go. There's a kind of a counterexample for you. Now, for E over Q such that E over QP has, I think that should say P, such that E over QP has bad reduction and E bracket P over QP has good reduction, okay, Weil studies rho EP as an Ord deformation of rho bar EP. That's how curves like this are handled, okay? However, even though we're in the Ord case, in the associated minimal deformation problem, there are flat methods used. There are finite flat group scheme methods used. I talked about this last video. It's not only the supersingular case that needs this finite flat group scheme stuff. There are specialized cases like this one, in the ordinary case where you have to invoke this theory. Okay, so here's another example for you. If E over QP has good ordinary reduction and rho bar EP is of the form omega star 0, 1, then the P torsion of the neuron model E over ZP of E over QP is a finite flat group ZP scheme with order P squared. It can be shown that cal E bracket P fits into a short exact sequence of finite flat group ZP schemes, and that sequence must take the form 0 to mu P to E bracket P to Z mod, constant scheme Z mod PZ to 0. Except in one case, which is the case when this E bracket P is isomorphic to mu P cross Z mod PZ constant scheme, in which there is also a sequence corresponding to the other way of splitting EP. Okay? How do you prove all this stuff? You can use the theorems of Raynaud from chapter 5. Okay? We'll be revisiting those theorems next video anyway. I'm not going to go into the details here because we don't really actually need this stuff. All right? So, yeah, I'll see you guys next video where we'll revisit and restate and kind of more highly concretize Raynaud's theorems because we're going to need them this chapter. All right, guys, thanks for watching, and I'll see you then.